Today we're going to talk about perpendicular bisectors and apply their properties. So a perpendicular bisector is a segment, a ray, a line, a plane, basically anything that is perpendicular to a segment at its midpoint. Equidistant means that a point is the same distance from two other points. So in this case, if we look at the example, they've got this perpendicular bisector here. I can see that from this perpendicular marking and the fact that this is therefore the midpoint. So what's going to happen here is we're going to have a perpendicular bisector theorem, which says that if we're on the perpendicular bisector, we're just as far from this point as we are from this point. So that's why that word equidistant is important. Pause here to write down any definitions if you need to, and then resume the video. So here are our perpendicular bisector theorems. So we've got the theorem itself and its converse. So if you remember, if both of those things are true, that means that we could write this as a biconditional statement. So a point is on the perpendicular bisector of a segment if and only if it is equidistant from the endpoints of the segment. So in other words, if we've got this point on the perpendicular bisector, it's always going to be equidistant to those 2 points. Or if we know that a point is already equidistant, then we can safely assume it's on the perpendicular bisector. Pause here if you need to jot anything down. So it says BD is the perpendicular bisector of AC. So automatically, I would probably go ahead and add both of those markings just to remind myself of that. And then it says, based on that, find the length of AD. Well, since D is on that perpendicular bisector, those two segments should be equal, which means my X value should be 7. So if I go back and plug that in, 5 times 7 tells me that AD has a length of 35 units. The next example says, in the diagram, WX is the perpendicular bisector of YZ. So YZ is being cut in half. I might want to mark that here. What segment lengths are equal? So we know YX is congruent to XZ, and we know YV is congruent to VZ, because they show that both of those with the 25, as well as YW would have to be congruent to WZ. And the reason I know that is that this point is sitting on that perpendicular bisector. I can also safely assume that V is sitting on that perpendicular bisector as well, simply because both of these have 25. So when it says, is V on that perpendicular bisector? Yes, it is, because it's equidistant from the 2 points. For each of these examples here, since this is a perpendicular bisector, we can assume that it's equidistant from the 2 endpoints. So for all 3 of these examples, all you're doing is setting each of these equations equal to each other. So I'm just going to do the first one with you. For practice, we get an X value of 3, and then I'm going to ask you to try 4 and 5 on your own, and then come back and check the answers. So pause here, come back when you're ready to check. And these should be your final answers. Now, technically, we did not answer what they were asking for, so be careful with that. They did want the length of AB, so AB should be 15. AB here is 30. And last but not least, 9 times 6 is going to be 54, so plus 1 is 55. So throughout this unit, the word concurrent is going to be really, really important. So a concurrent point is a point where 3 or more lines intersect. So a point of concurrency is where 3 or more lines intersect. So if you look at this picture here is the only one that is concurrent, meaning they all meet at that one point. 8 and 9 are not, because they meet at 2 different points here, and they don't intersect at all in picture 9. So picture 7 is the only one that is concurrent. Pause here if you need to, and then we'll move forward. So a perpendicular bisector of a triangle, all of those perpendicular bisectors, if we drew them for every single side of the triangle, they're going to meet at a point of concurrency that we're going to call the circumcenter. The segments from the circumcenter to the vertex are always going to be congruent. We're going to have a little bit more information to fill in as we go. So this unit is going to be really heavy on memorization. So what we want to start associating are perpendicular bisectors with their point of concurrency, which is called the circumcenter. So if you look at this, they've drawn an acute triangle. This point right here where all of those lines meet, or all of those perpendicular bisectors meet, that's the circumcenter of that triangle. So in an acute triangle, the circumcenter is inside the figure. For a right triangle, it's at the midpoint of the hypotenuse. And in an obtuse triangle, the circumcenter is outside the figure. And those are going to be important to us in terms of where can this point be located. So in this case, a circumcenter created by the perpendicular bisectors can be inside, on, or outside the figure. Pause here if you need to. There's one final little piece here that says segments are congruent from the circumcenter to the vertex. So from here to the vertex is the same as from here to the vertex is the same as from here to the vertex. Same thing here, same distance, and same distance. And here as well, same distance, and the same distance. So that's a key property of a circumcenter, that it is the same distance to every vertex. So again, the circumcenter has that name because with that point, we can circumscribe a circle around the outside of the figure with that point of concurrency, the circumcenter, being the center of the circle. So when we circumscribe something, it goes around the outside of that figure. So if you'll notice, from this circumcenter, we have touched all 3 corners of that figure and drawn a perfect circle around it. Same thing for the right triangle. We've used the center to perfectly touch all 3 or circumscribe this triangle. Same thing for picture 3. So another property of the circumcenter is it is the center of the circle that would perfectly fit around the vertices of this triangle. So, the perpendicular bisectors all meet at point G. Find the indicated measures. So this right here is our circumcenter. So remember that that point is formed by the perpendicular bisectors. So I can assume that that's a perpendicular bisector, that this is a perpendicular bisector, and that this is a perpendicular bisector. I can also safely assume that it's the same distance to each vertex. So if one of those distances is 9, then BG is also 9. Same thing over here, G to A would have to be 11 because G to C is 11. I also would know a couple of other key pieces as well. So as you're kind of going through this, you want to think about what are the information pieces you're given and what do you know based on the fact that this is a circumcenter. Last but not least, we want to take these 3 vertices and find the circumcenter. So remember that the circumcenter is formed by the perpendicular bisectors. So what I want to think about is how do I find a point that is both perpendicular and bisecting these three sides. So I'm going to start with 5, -3, -1, 3, and 7, 5. So those are my 3 points. I'm going to connect them together as a triangle, and then I'm going to create my perpendicular bisectors. So a bisector means that I need to find the point in the middle, meaning the midpoint. So what I'm going to do is I'm going to first find the midpoint of 2 of the sides. I could do all 3, but because this point of concurrency is where all of these lines are going to meet, I really only have to do 2 of the sides. So I might first find the middle of ED. So remember, for midpoint, we always average those numbers together, meaning if I add my x's of D and E together and divide by 2, and if I add my y's together and divide by 2 for D and E, that'll tell me where my midpoint is. So my midpoint is at 2, 0. And I should be able to plot that, and it should fall on my line. Now I'm a human, so there's a little bit of error there, but I can see that that's pretty close to where that needs to be, so that should be in the correct location. I may also want to go ahead and mark that that means those 2 parts are equal. I also need to find the midpoint of one other side, so I'm going to find the midpoint of EF. So using E and F, -1 plus 7 divided by 2, and 3 plus 5 divided by 2. Again, what we're doing there for the midpoint formula is we're adding the x's and dividing by 2 and adding the y's and dividing by 2. So in this case, we've got 3, 4. So on my graph at 3, 4, that's pretty close. Again, I'm a human, so that line's not perfectly going through there, but I'm going to go ahead and mark that these 2 are congruent as well. So if I'm thinking about the perpendicular bisector part, I've taken care of the bisector. I found the middle. So now I need to create a perpendicular line. So step 2 is create a perpendicular slope to each of those sides. So if I'm looking at ED and I want to know the slope of that, I'm going to look at its rise over run. So from E to D, we're going down 1, 2, 3, 4, 5, 6, and we're going right 1, 2, 3, 4, 5, 6. So that means that with a slope of decreasing 6 and running 6, that's a slope of -1. So the perpendicular slope to that would be +1, which means from that point on ED, I'm going to apply a slope of 1. So up 1, right 1, up 1, right 1, up 1, right 1, and so on. And I'm going to get a couple different points on that line so I can sketch that as close to perfect as I can. And as soon as I do that, I've created a perpendicular line. So I'm going to add that 90-degree angle. I need to do the same thing for the slope of EF. So looking at EF, that's a rise of 2 and a run of 1, 2, 3, 4, 5, 6, 7, 8. So up 2 over 8 tells me that that's a slope of 1/4. So my perpendicular slope to that is -4. So from that point, I'm going to go down 4 and right 1. I'm also going to go up 4 and left 1. So that what that's going to do is it's going to give me a line that goes through here. Now, as we can see, we can tell that these are crossing, but they're not crossing at an exact location. Now, on a test or quiz, I would make sure that they do cross at an exact location for you. However, in this particular case, if it's not a precise coordinate where they're crossing, then what I would need to do is write the equations of both of these lines and then use either substitution or elimination to solve. Now we're going to practice this a little bit more throughout the rest of the week, and like I said, I would make sure on a test or quiz that they cross at a definitive location for you. So hopefully this process just to get us started will kind of help a little bit, and we will circle back to this at a future date. If you have any questions or concerns about anything as you work, please let me know. Otherwise, have a great day.